Welcome back, everyone. Surprising to many, climate change over the past 10,000 years has acted completely opposite of what the CO2 hypotheses predicted. So here in part 4 of my educational video series, I present a much-needed alternative hypothesis that is 100% supported by evidence over the past 10,000 years. I call it the dynamic warm pool La Nina intertropical convergence zone hypothesis, or just the warm pool theory for short. As Rosenthal in 2016 argued, it only requires very small changes in solar heating to amplify major atmospheric circulation changes. The Earth's average temperature is a balance between heating from absorbed solar energy and the rate of cooling as that energy is radiated back to space. The warm pool theory argues ocean dynamics determine the Earth's heat storage and heat ventilation, and that's what controls the Earth's rate of cooling. The function of the warm pool is analogous to a home's hot water heater and determines how much heat reaches the rest of the world. When a home's hot water heater is fully charged, then there's adequate hot water for every sink, dishwasher, and shower. But drain that hot water heater and you suffer a cold shower. Warmer water gradually returns as the hot water heater recharges. Likewise, the Little Ice Age drained the warm pool, and now our current warming trend is simply the net effect of a recharging warm pool. Because oceans can store huge amounts of heat, but the atmosphere cannot, and because the upper 10 feet of the world's oceans contain more heat than the entire atmosphere, solar-driven ocean dynamics are truly the climate control knob. The warm pool theory explains the past 10,000 years of climate change, an explanation that CO2-driven climate models have repeatedly failed to account for. The Indo-Pacific Warm Pool is often called the heat engine of the world. It is defined by waters that are 28 degrees centigrade or 82 Fahrenheit or warmer, and is primarily located in the Western Pacific as well as the Eastern Indian Ocean. The intense convection over the warm pool drives the region's Hadley circulation and transports heat via the atmosphere from the tropics towards the poles. Convection requires a minimum ocean surface temperature of 26 degrees, and widespread deep convection requires 28 degrees centigrade or more. Smaller warm pools will generate less convection, and thus less global warming. In addition, the strength of the warm pool also determines how much water is transported from the tropics to the Arctic via several dynamics that integrate into the global conveyor belt. It is well established that on average the tropics receive far more solar energy, represented by the blue curve, than the tropics radiate back to space, represented by the red curve. That's because significant tropical heat is transported to the poles, where it is radiated back to space. That transported heat also warms the poles, which become much warmer than by solar radiation alone. Thus, a stronger warm pool generates a higher global average temperature by transporting heat across the globe via convection and the ocean conveyor belt. Several peer-reviewed papers have examined how the warm pool has changed since the last glacial maximum. The illustration here is from Dang 2020. Despite low CO2 concentration, temperatures in the warm pool began heating up 25,000 years ago and peaked about 10,000 years ago in a period known as the early Holocene. Then for the past 10,000 years, the oceans cooled until a slight warming trend began over the recent 300 years. In contrast, sea surface temperatures and the global average temperature lag behind the warm pool warming, and that suggests it is deep ocean warming that drives atmospheric warming. The Sun's Milankovitch orbital cycles of obliquity and precession seem to correlate well with the warm pool's long-term temperature trends, but can't explain the last few hundred years. Those orbital cycles do not add to the Earth's annual insolation. The peak of those cycles in the early Holocene did cause warmer northern hemisphere summers, but were balanced by colder winters. In addition, if precession drives global temperatures, our current temperatures should be as cold as they were 22,000 years ago. Now, I introduced the mechanics of these cycles in part 3 of this series, how the sun and the ITCZ control the climate in civilization collapses. Cooling of the Holocene warm pool can be explained by the ITCZ's southward migration that increases El Nino events, which ventilate and drain warm pool heat. The ITCZ integrates global energy inputs and outputs, and accordingly shifts the average location towards the warmest hemisphere. Thus, small changes in solar energy can drive the migration of the ITCZ. As the ITC migrated southward, it increased the frequency of El Nino events that cooled the warm pool and contributed to the Holocene cooling trend. Conversely, it can be inferred that any northward ITCZ shift would result in fewer El Ninos, and more La Nina-like conditions that enlarge and warm the warm pool. Although the exact reconstruction of global temperatures vary depending on the models and data that a researcher employs, all agree there has been an 8,000-year cooling trend, and that is the exact opposite of what CO2-driven climate models simulate. The erroneous climate models are driven by an 8,000-year trend of increasing CO2, which puts those models at odds with evidence-based climate change. In contrast to the Holocene cooling trend, all relevant researchers have found the warm pool has been expanding since 1900. And this expansion coincides with a more La Nina-like Pacific Ocean, with fewer El Nino events than during the Little Ice Age. Here is a closer look at the dynamics that control the warm pool and the effects of the ITCZ and El Ninos. Trade wind-driven equatorial currents bring heated water to the warm pool. These currents are the North Equatorial Current, designated here as NEC, and two branches of the South Equatorial Current, designated SEC. The equatorial currents generate higher sea levels in the Pacific, which pushes warm water through the maze of channels around the islands of the maritime continent, comprising a westward current known as the Indonesian throughflow. Much of that throughflow joins the Indian Ocean's South Equatorial Current that is part of the ocean conveyor belt. Now, some throughflow water circulates through the northern Indian Ocean, enhancing an Indian Ocean warm pool. While some flows join the Leeuwin Current that flows southward along the west coast of Australia during a strong La Nina, this current is amplified, producing what Australians call a Ningaloo Nino. Now, while the warm pool's overflow through the Indonesian throughflow modulates its size, it is the eastward north equatorial countercurrent that truly controls the warm pool's size, which then modulates the throughflow and the warming of the ocean conveyor belt. The stronger the north equatorial countercurrent, the more rapidly the warm pool is drained. The strength of the North Pacific gyre controls the draining of the warm pool. The gyre is driven by the north trade winds that drive the north equatorial current on the gyre's southern border, while the westerly winds drive the gyre eastward on the gyre's northern border. The northern equatorial current contributes a limited amount of water to the warm pool because much of the current veers northwards into the Kuroshio Current, bringing added warmth northwards to Alaska. Since the 1980s, many researchers have reported that a strong gyre drains the warm pool by enhancing the countercurrent. Most recently, researchers confirmed the connection between the gyre strength, the southward ITCZ migration during the Little Ice Age, and an enhanced countercurrent that drained the Little Ice Age warm pool. So, what's the role of the ITCZ? In the age of satellites, the ITCZ is defined by a band of heavy clouds encircling the Earth. But centuries ago, sailors identified the ITCZ by the doldrums, which stranded many a ship for days and weeks. The ITCZ's vertically rising air creates a relatively motionless surface air with no movement to the east, west, north, or south. Thus, the doldrums allow a countercurrent to flow eastward without being opposed by the westward trade winds. As a result, a shifting ITCZ can determine the strength of the countercurrent and the size of the warm pool on all time scales from seasons to ice ages. The two branches of the south equatorial current provide about 66% of the warm water to the warm pool. Because the ITC's average position over the Pacific remains to the north, there is only a very weak south equatorial countercurrent, here designated as SECC. That sometimes disappears completely, so equatorial countercurrent has a minimal impact on the warm pool. Not only does the ITCZ drive the strong north equatorial countercurrent, but also a deeper eastward undercurrent that drains the deeper waters of the warm pool. So how does the sun and greenhouse warming affect the warmth of the equatorial currents? The warm pool waters originate from the high pressure regions in the eastern Pacific created by the Hadley circulation. The descending air in those high pressure systems are dry, and thus few clouds are formed, and that amplifies solar heating. The lower amounts of water vapor, the major greenhouse gas, also allows more heat waves to escape back to space, reducing any greenhouse warming. So it is accurate to claim increasing warm pool heat is driven by solar heating. Now, all the dynamics in a La Nina-like ocean are illustrated here. An official La Nina happens when temperatures in the Nino 3.4 region are at least a half degree Celsius cooler than average for 3 months. Whether during a neutral El Nino oscillation year or an official La Nina year, the same dynamics increase the warm pool. Accordingly, the Western Pacific experiences higher sea levels that feed the Indonesian through flow and ocean conveyor belt. More warm water gets stored deeper in the West Pacific warm pool, deepening the thermocline. Strong trade winds cause upwelling of cooler deep waters in the Eastern Pacific, causing a large east to west temperature gradient of about 6 to 7 degrees Celsius between the warmer western warm pool and the cooler upwelled waters of the Eastern Pacific. That large temperature gradient defines a La Nina-like ocean. This temperature gradient amplifies the trade winds, which further reinforces La Nina conditions. All climate models based on the physics of CO2 warming have predicted that rising CO2 would have little effect on the warm pool surface temperatures, arguing CO2 would preferentially warm the Eastern Pacific, where dryness had reduced the greenhouse warming, and thus reduce the temperature gradient. But that has never happened, as the large temperature gradient has on average remained or increased in accord with the currently growing warm pool. In 2019, Seeger published a paper to resolve this problem, showing that by using different physics, the lack of Eastern Pacific warming was actually consistent with CO2 theory. Apparently, the choice of which science to follow is quite arbitrary. So with amplified trade winds maintaining strong La Nina-like conditions, what triggers the switch to an El Nino every 3 to 7 years? The short answer is the ITCZ. The ITC doldrums enabled an amplified eastward equatorial countercurrent that results in El Ninos. As the ITCZ moves southward, the rising air within the ITCZ also triggers the intense convection in the Indian Ocean, of the 60 to 90 day Madden-Julian oscillation that produces westerly wind bursts. Those westerly wind bursts can initiate a Kelvin wave of eastward flowing warm pool water. The resulting El Nino events then drain the warm pool and cool the ocean's subsurface waters. Enough 26 plus degree warm pool water moves eastward to also shift the location of intense convection affecting global weather. The warm pool's stored subsurface heat is brought to the surface in the central and the eastern Pacific, where it ventilates, causing a temporary spike in the global average air temperature. That reduces the east-west temperature gradient, which defines an El Nino-like ocean. A smaller temperature gradient weakens the trade winds, reducing the volume of warm water being pumped into the warm pool. Upwelling is reduced in maintaining a warmer eastern Pacific. And with added water vapor over the eastern Pacific, the ocean absorbs about 15 watts per meter squared less energy, further cooling the warm pool. Now, looking at just the past 2,000 years, Oppo's 2009 temperature reconstruction shows the recent warm pool temperatures, shown here in black, that began increasing in the 1700s before the rise of industrial CO2. Oppo also compared the warm pool trends to Michael Mann's 2008 global temperature reconstructions, shown in red. Both reconstructions show similar long-term variations, except Mann's last 100 years that he attributes to the rising of CO2. However, the warm pool was warm 1,000 years ago during the medieval warm period, and it was as warm as it is today despite lower CO2 concentrations. However, the warmer medieval warm period does correlate with a La Nina-like ocean and an ITCZ that was located much further north. During the Little Ice Age, the warm pool cooled, associated with sunspot minimums and the southward migration of the ITCZ. The ocean entered an El Nino-like state, as indicated by coral proxies from Cobb 2003 and other researchers, indicating ocean dynamics were draining the warm pool. Since the 1700s, as the ITCZ moved back northwards, the ocean experienced fewer ventilating El Ninos, and the warm pool began warming and expanding. So here's how to interpret a graph of the past 50 years of global average temperatures. Putting aside changes in land surfaces that also increase temperatures via dynamics such as the urban heat islands, the most parsimonious explanation for the observed warming trend is there are currently fewer El Ninos than during the Little Ice Age, and more La Nina-like years that has increased the heating dynamics to support a growing warm pool. The warming trend simply reflects the recharging of the Earth's hot water heater that was drained during the Little Ice Age. The transitory temperature spikes are caused by El Nino's discharging of stored heat, which temporarily cools the ocean. So what does the future hold? It's hard to know. The scientific community is completely divided on predictions regarding more or fewer future El Ninos. But the next few decades should provide some evidence that could refute or support the warm pool hypothesis. So teach your children to be on the alert and think critically. If low solar output continues with low sunspots, as some predict, then if the ITCZ is truly sensitive to such small radiative changes, the ITCZ would move further southward and temperatures will approach the Little Ice Age conditions. However, if solar output increases as others predict, the ITCZ should edge northwards and the warm pool will continue to expand and temperatures will approach those of the medieval warm period. The good news is, since there was no climate crisis 1,000 years ago, there won't be one that happens in the near future. and the effects of CO2 will continue to be insignificant. So up next will be part 5, how pressure systems control the climate, the cause of heat waves. And until then, embrace renowned scientist Thomas Huxley's advice that skepticism is the highest of duties and blind faith the one unpardonable sin. And if you appreciate the science clearly presented here, science rarely presented by mainstream media, then please give it a like, give it a share, or copy the video's URL and email it to friends. Subscribe to my channel to keep in touch with all my videos, or read my book, Landscapes and Cycles, An Environmentalist Journey to Climate Skepticism. Thank you.